So we left off yesterday with learning how to calculate the expected counts. We want to think proportionally about this if the distributions were the same, because that is our null hypothesis. So the first thing that we did was we found the proportion of all of the gummy bears that were red. We had 151 total gummy bears out of 560. So we got what percent of all the gummy bears were red. And then we took that value and we figured out what 27% of all the Haribo gummy bears would be. That's where we got this 89.91. And then we figured out what 27% of all of the Kroger gummy bears was going to be. That's where we got this 61.29. And obviously we have a little bit of rounding error in here, but it adds up approximately to 151. We got it to add up to like 151.2, right? All right, so we can do that for all the other cells. However, I want to talk about like a slightly faster way of calculating this, or at least another way of thinking about it. Instead of doing this in two steps, where first I find the percent, and then I multiply it by all the Haribo, then I multiply it by all the Kroger brand. If I take a value like 5, I divide that by 8, and then I multiply the whole thing by 7. What do I multiply by 7 if I'm just doing something like this? Does it multiply to both pieces? Just the top, right? So here, I'm taking my fraction, and I'm going to multiply it by something else. So an easier way for me to remember this is that my expected counts, I'm going to take the row total, that was my 151, times my column total, the 333. So I'm multiplying these two pieces together. And then we're going to divide by the table total. So that's how you find your expected counts when we have multiple categories for two different things. In this case, it was type of gummy bear and then color. I would like you guys to finish filling in the table. Let's take about, let's see, you guys have 6 colors left. Let's take about 3 minutes for you guys to finish filling in the table. If we don't end up needing that much time, that's okay. Let's take about 3 minutes and finish filling in the expected counts for the table. It has no eraser, but it has lead. So fill in the remainder of the expected counts. Mm-hmm. So the reason that it's going to come out slightly different, do you remember when we got that 0.27 measuring around to get 0.27, 0.269 something. So when you do it in the way that's written out in green, it's going to be more precise because we're not rounding that percentage first before we multiply. Good. Okay. It's statistics. Horseshoes and hand grenades, it's close enough. What'd you guys get for green Haribo? 78.49. What about yellow Haribo? You said what? 57.09. Did you get the same thing?
No, I got something slightly different.
Okay. Okay. What about orange Haribo? You said 63.03? White Haribo. You said 29.14? All right. Blue Haribo. You said 8.96? 92? 8.92. And purple Haribo? 6.54. Let's do some Kroger ones now. Green Kroger brand? 53.51. Yellow Kroger? 38.91. Orange Kroger brand? 42.97. White Kroger brand? 19.86. Blue Kroger brand? 6.08. And purple Kroger brand? How much? 4.46. So, do you guys remember what our conditions were when we were doing the goodness of fit test, or for anything that we've done conditions on? What are the three things we need to check conditions on? Randomness, independence 10%, large counts, general shape, yes. Randomness and 10% condition don't really change for any of our tests. Large counts, or shape of the distribution, did change on this. We don't care now, and we don't want it to be approximately normal. We want it to be what shape? Approximately chi-squared, yes. And what are we looking for with our large counts to check that it's approximately chi-square? All of our expected counts have to be greater than or equal to 5. Did we hit that? No. We're going to go ahead and run the rest of this so you guys get experience going through the 4-step process with this, but technically speaking, we can't continue on because all of our expected counts are not 5 or larger. So we're going to make note of that when we do our conditions, but then we're going to go ahead and run the rest of the test so that you guys have some experience with doing that. Fair enough? Okay. Thank you. Thank you, thank you. Let's go ahead and flip the page. We're going to do a 4-step significance test. What significance level should we use? 0.05, yes, alpha equals 0.05. What did we say our null hypothesis was? Absolutely correct. There's no difference in the color distribution for Haribo and Kroger gummy bears. And I forgot to label that as my null hypothesis, so let me get that in there. There we go. And our alternative hypothesis? Yes. There is a difference in the color distribution for Haribo and Kroger gummy bears. What we are going to perform is called a chi-square test for homogeneity. Last time, we did a goodness of fit test. 12.1 was goodness of fit. For goodness of fit, I had to have some idea. I had to have a claimed distribution that I was comparing my sample to. With a chi-square test for homogeneity, do we have information from Haribo about how their color distribution is? No. Do we have information like that from Kroger? We are just comparing these two to see if they have the same distribution. I don't know what the exact distribution is of either one. I don't know what the claimed amount is. I want to see if they have the same distribution as each other. That is what my chi-square test for homogeneity is going to be. So checking our conditions. We have random. Independence are 10%. And we have large counts. All of my expected counts need to be 5 or greater. Do we get randomness? Yes, why? Yeah, we're going to assume that each of those bags of gummy bears is an independent random sample from these two companies. They need to be independent of each other. To the best of my knowledge, whoever makes Kroger gummy bears is not the same people that make the Haribo gummy bears. So these are independent samples. And they are random samples. They fill those bags randomly after they mix them all together so that you get a nice smattering of all the different colors. Why do we care about randomness? Yes, so we can generalize. So that, what would the populations be? Kroger and Haribo gummy bears. Yes, all Haribo and Kroger gummy bears would be my populations. Independence. How many total gummy bears did we have? 560. Should we do it as 560 is less than or equal to? How many samples did we pull? We pulled 2 different samples. So what should we check here for our 10% condition? Yep, 333. Yes, is less than or equal to 0.10 of all Haribo gummy bears. I'm going to use GB for gummy bears if that's okay. So there has to be at least 3,330 Haribo gummy bears. Do you think that's a pretty safe assumption? Yes. So now we still have to come back in and check Kroger. We had how many Kroger gummy bears? 227, less than or equal to 10% of all Kroger gummy bears. So that means there has to be at least 2,270 Kroger gummy bears. Safe assumption? Yes. So we are good on our independence. Why do we care about it being independent? So we can what? Sorry, I still can't hear you. My apologies. It's so that we can use our formula for standard deviation. It's so that sampling without replacement doesn't change the population distribution. We're not messing up the population distribution by consuming that one bag of gummy bears. We've taken them out of rotation, but it is so small compared to the total population that we didn't change the overall population distribution by taking those ones out. That's what we're checking for with this 10% condition. Because I want to make sure that whatever I'm doing, I can generalize back to my populations here. If I take too many and eat them, then I've fundamentally changed the whole distribution of that population. Large counts, all expected counts greater than or equal to 5. What was our lowest? 4.459 or 4.46, right? Technically, we should stop here. I'm going to make a little note of that. For what we're doing here, we're going to round up. But if you're doing this on an AP Stats test, no, you would not round it. You would say, we don't meet the large counts condition. We cannot continue on with this test. Mm-hmm. So technically, we don't meet this condition. We should stop. However, I need you guys to have some experience with this test, so we're going to go ahead and finish this test out. This is so we can check to see that our sampling distribution is approximately chi-squared. So far, so good? All right, we got state out of the way. We got plan out of the way. Now for do. What is the formula that we used last time?
Sum of all observed minus expected value squared over the expected value.
Absolutely correct. We're going to do the sum of all. That's that weird, like, almost E-looking thing. That's a sigma. Observed minus expected squared divided by the expected. All right. I'm going to show you guys a little bit of a shortcut for writing down our work, and then I'm going to show you how to do this in lists in the calculator. So we're only going to write down some of these fractions, because in total we're going to have 14 fractions. I do not want to write down 14 fractions that all have this subtraction and then squaring and dividing. So let's grab just a couple of them. You can do the first one and the last one, as long as you put the pluses and the dots in between to indicate that there's these other pieces that we're leaving out. Or I like to do the first two so that you kind of know what order somebody's going in, and then show the last one. That's perfectly fine. What was our observed number of red Haribo gummy bears? How much? 105. What was our expected for the red Haribo gummy bears? You said 89.79? So close my parentheses, square it, divide by 89.79. And then let's go do green Haribo gummy bears. What was the expected, or what was the observed for green Haribo? 73. And what was our expected? 78.49. Close my parentheses and square it over 78.49. And now let's go do the very last one, which is what? Purple for Kroger. What was our observed purple gummy bears from Kroger? Observed from Kroger? We had 11 observed. What was our expected purple from Kroger? 4.46 or 4.459. So we're doing all of them, but we're not writing down every single fraction. From both of the brands, yes. We have to do all 14 fractions. I'm going to show you guys how to use the lists in the calculator to make this faster. You'll still need to write down all of those values because we're going to have to see which piece is the largest in case we need to do a follow-up analysis. But writing down 14 numbers is very different than writing down 14 fractions that have the squaring and all whatever. All right, so grab your graphing calculators. Stat, edit, list 1. Clear out anything that you have in your lists already. All right. Stat, edit. My lists have stuff in them, so I need to clear them out. All right. Down list 1. Decide whether you're starting with Haribo or Kroger, but we're going to put all 14 numbers in list 1. I would like to do all the Haribo straight down the list and then all the Kroger. We do have to include those zeros. So going back to our observed, we had 105 red Haribo. We had 73 green. We had 65 yellow, 50 orange, 40 white, 0 blue, and 0 purple. I'm going to keep adding to this same list. We're going to go up to the top of the Kroger list now and do Kroger red and then go straight down. So we had 46 red Kroger gummy bears, 59 green, 31 yellow, 56 orange, 9 white, 15 blue, and 11 purple. Notice my very last one tells me I'm entering this in cell 14, so I made sure I got all of them. So far, so good? All right. Now we're going to go over to list 2. And we have to make sure that we enter our expected values in the same order that we entered our observed. So this is why you have to think about like which order are you putting them in. So we're going to start with red Haribo and do all the reds. So my expected count for red Haribo was 89.91. And then 78.49 for green. 57.09 for yellow. 63.03 for orange. 29.14 for white. 8.92 for blue, 6.54 for purple. Make sure this is matching up with your other list. I had 0 observed blue and purple, so I'm making sure that my blue and purple expected counts are going right here. Now I'm going to start back up at the top of the list with Kroger, 61.29 for Kroger red. 53.51 for Kroger green, 38.91 for Kroger yellow, 42.97 for orange, 19.86 for white, 6.08 for blue, and 4.46 for purple. You should end at the same space right here. Double check your list, make sure that they're lined up. If they're not, you're going to get a dimension mismatch and your calculator won't go any further on this process. All right, everybody have all their numbers in these 2 lists. All right, we're going to go over here to list 3 now. And you need to arrow up so that you make the L3 highlighted, like this. All right. We're going to give it a formula for list 3. Anybody ever worked with Excel and formulas in Excel? That's basically what we're going to be doing here on a much lower level. So we are entering a formula that we want it to calculate with everything here. Open up parentheses first, and you'll be able to check what we're entering right down here. Second and 1, there's all my numbers from list 1, minus second and 2, close your parentheses. You have to put the parentheses. So parentheses L1 minus L2, that is my observed minus my expected. And then what are we going to do to the observed minus expected? Square it. This is why the parentheses are essential. You want it to square the difference, not just square the expected. And then what are we going to do to it? Divide by L2 because that's my expected. So second 2. If you hit enter, it should populate the entire list. Those are the 14 numbers that you need to write down and then add together. But it did all of the subtraction, all the squaring, and all the dividing for you. So let's go ahead and write those down. Nope. As long as you write down those fraction pieces like I showed you, that like you write down the first one plus ... in the last one, or the first 2 plus ... in the last one, that's sufficient. They understand that you have used some kind of technology or you just did it on your calculator over and over and over from there. All right, so I'm going to go through and write these all down. So my first value, let's take it out to 2 decimal places. So 2.53 plus 0.38 plus 1.1 plus 2.69 plus 4.05 plus 8.92 plus 5.64 plus 3.81 plus 0.56 plus 1.61 plus 3.95. Make sure you scroll down so that you get all of them. Because 3.95 only takes me to 11. I got to keep going. 5.94. 13.09. And 9.59. All right, I'm going to need some help adding up all of those values now. There is a sum formula that you can use on the graphing calculators. I don't remember exactly where that formula is, but there is a sum formula. You can make it add an entire list for you. Come on, there we go. Right. When you guys have a sum, please let me know. You do need to write them all down when you do an FRQ.
Yep.
Yep.
They're just for right now.
So you should have 14 values written down. You need to add those 14 numbers. Tell me what you get when you add those 14 together.
I figured it out. It's second stat, and then you arrow over to math, and there should be a sum option.
Second stat.
Oh, well, listen, I'm going to figure it out.
Yeah, I
Right?
wasn't typing it all out my head.
I don't blame you. Second and stat. Over to math.
Yep.
And then we have sum, so option 5. And we want it to sum list 3, right?
Yep.
So second 3. Oh, it just replaced my last value. I got 64.77, but it replaced my last value on there.
Oh well.
Hold on. 9.59 is what should go here. Make sure you're in an open cell. There we go. Second stat, over to math. We want the sum, and I want it to do all of list 3. Yep, I got 64.77. All right. Who's having trouble getting that to work?
Me.
Okay.
How do you keep saying that?
It says dimension mismatch. Okay, you need to arrow down until you're actually in a cell. So stat, edit. There you go, you're in an open cell. So now second stat, over to math, sum, and then second 3, and then hit enter. There we go. Anybody else having trouble?
Over to math, and then go to 5.
Yep, option 5. Oh, you don't want to be there. Here, you want to be in an open cell.
So
let's quit what you were doing there. Stat, edit. Okay, we're going to arrow until you're in an open cell, like right here. Okay? So now second stat, arrow over to math. Option 5. Yep. And then second 3, because that'll get you all of list 3.
And then close the parentheses.
And then hit enter. Your numbers, oh yeah, I don't know what's up with that right there. Something got entered wrong. What was your list 1 value there? 105.89. Let me figure out what happened.
Numbers to figure out which one's wrong.
That's okay. I know that first one is wrong, so I cleared out your list 3. We're going to re-enter that formula.
Okay.
So parentheses, second 1 for L1, minus second 2 for L2, close of square, divided by L2. Oh, 2.53, I got it. It looked like it said 2,000 something. Okay, so second stat, math, option 5. Oops. Second stat, math, 5. We wanted to add list 3. Yeah, something got messed up in one of your lists. Okay. We can find it later, though. All right, most people, are we getting approximately 64.77? Awesome. We need degrees of freedom. Degrees of freedom, when I have a two-way table like this, because we're looking at more than one sample, we do the number of rows. How many rows did we have? We had 7 rows, right? Because we had red, green, yellow, orange, white, blue, and purple. So 7 rows. And then columns. How many columns did we have? We had 2 columns, one for Haribo, one for Kroger. All right. We're going to subtract 1 from each of those. So I'm going to have 6 times 1, which means how many degrees of freedom? 6 degrees of freedom. All right, so chi squared with 6 degrees of freedom. My test statistic, my chi-square is 64.77. If this is 0, where do you think 64.77 would be?
Way off that tail.
Way over here somewhere, 64.77. I'm going to write down my test statistic. Chi-squared equals 64.77. To find the p-value, what do we do? Yep, chi-square CDF. What's my lower bound? 64.77. There's my lower bound. Upper bound? Some outrageous number. There's my upper bound. And 6 for my degrees of freedom. Tell me what you get for your p-value. 4.8 times 10 to the negative 12, you said? Which means if I were to write that out longhand, that's about what? As pretty much 0. Still, when I do my conclusion, I'm not going to use 0. I'm going to use this. Make sure you're writing it in scientific notation. Don't write an E. They don't want to see an E on the test.
That's the p-value?
P-value is 4.8 times 10 to the negative 12 on the calculator by doing this. Chi-square CDF. Chi-square CDF. Ooh, no. You put 6.77. It's 64.77. That'd make a big difference because, yeah, that'll give you a very different p-value. All right, let's conclude. Tell me how to start my conclusion. All right, I'm going to slow you down real quick. I like almost everything I heard. Assuming the HO is true, we don't have a claimed distribution this time because we don't have a distribution that came from a company and they're like, this is what we're doing. We're not checking it against some claim. What are we doing? Checking it against the other. And I don't technically know the distribution of either one. So what was our HO? there is no difference in the distribution of Haribo and Kroger gummy bears. We get a shortcut on the fractions, but we get no shortcut on this one. So assuming the Ho is true, there is no difference in the distribution of Haribo and Kroger gummy bears. There is a, what was our p-value again? 4.8 times 10 to the negative 12 probability of getting chi-square of 64.77 or larger purely by chance. Because what? (4.8 times 10 to the negative 12 is less than 0.05. Ran out of room on my screen. I'm going to bump that down to the next line because I can't see that at all. 4.8 times 10 to the negative 12 is less than 0.05. We what? We reject the Ho. Shh. And do or do not find convincing evidence? We definitely do. And find convincing evidence that what is true? There is a difference. In the distribution of Haribo and Kroger gummy bears. Because we decided to reject the Ho, what do we have to do? We have to do a follow-up analysis. So I'm going to have to write that down at the bottom. I ran out of room. Down here for my follow-up analysis. You do not. The largest component of chi-square is what? Which one was our biggest chi-square? What'd you say? Well, let's go look. Let's look at the numbers that we added together. This is what we're looking at here. Which of these is the largest component? 13.09. So that's what we're going to use for our follow-up analysis. Oops, went too far. Not far enough. Is 13.09 because that 13.09 went with which piece? This is the other reason why it's really important to know how you put that in the calculator. The blue Kroger band. Was it way more or way less than expected? Way less, right? What did we expect? Blue Kroger band, we expected 6.08. How many did we actually get? How many blue Kroger gummy bears did we see? 15. We expected 6.08. Is what we observed way more or way less than what we expected? Way more. Because the number of blue gummy bears, blue Kroger gummy bears, was far more than expected. Mm-hmm. Yes. Because we're basically talking about which piece in all of this contributed the most to why we have such a large chi-squared. Does that make sense? A lot of times it's coming from one particular part. All right, to wrap us up for today, also, homework's not due tomorrow. Homework's due Monday. We've talked about two different tests that are both chi-squared. Test for homogeneity and test for goodness of fit. How is the test for homogeneity, what we did with the gummy bears, different than the goodness of fit, the M&Ms? We were looking at color with both of them. Yes, we had a claim distribution, and how many samples? One sample from one population compared against a claim distribution. Chi-square test for homogeneity, like we did with the gummy bears, we had a variety. How many samples did we have? We had two samples, one from Haribo, one from Kroger. How many variables were we looking at, though? Just one. That's okay. No, I know why you said 7. It's because it's a categorical variable. It has 7 categories, but it's just one variable. It's just the color of the gummy bear. We had 2 samples from 2 different populations. We're going to do the check your understanding right at the beginning of class tomorrow before we go and look at our last type of chi-square test. There are 3 total chi-square tests. We've talked about goodness of fit and homogeneity. Tomorrow we'll practice another with homogeneity right at the beginning. And then we'll talk about the last kind of chi-square test, which is a chi-square test for independence.